Hello learners, welcome back. I am Rajat Tiwari, lecturer, University Teaching Department, Chhattisgarh Swami Vivekananda Technical University and subject matter expert for this course. In today's session, we will explore the critical topic of sound insulation and ventilation in buildings. We will delve into the essential aspects of acoustics and air quality in building design, examining how effective sound insulation can enhance comfort and privacy, while proper ventilation ensures a healthy indoor environment. This session aims to provide you with a comprehensive understanding of each element's role and importance in creating efficient, comfortable, and safe building environments. In this session, we will discuss the following key points, which include the sound insulation, classification of noise, noise transmission, sound insulating material, ventilation, functional requirement of ventilation system for human comfort, and air conditioning. So now let's discuss what is sound insulation. Sound insulation prevents noise transmission between rooms or from outside. Noise, often caused by high frequency or intense sounds, can lead to discomfort in various issues like discomfort and annoyance, adverse effect on blood pressure, muscle strain and sleep, fatigue and reduced efficiency, diminished quality of music and speech, disruption of concentration, potential for temporary deafness or nervous breakdown with prolonged exposure, and increased productivity with reduced noise. Actually, noises can be classified based on their origin into two types. First one is outdoor noises and second one is indoor noises. So, outdoor noise these originate from source like road traffic, railways, airplanes, moving machinery and nearby factories, while indoor noises come from sources within the same or adjacent room such as conversations, moving furniture, crying babies, radios, musical instrument, sustain operations, typewriters and door slamming, etc. Alternatively, noise can also be categorized as airborne noises and structure-borne noises. So, airborne noises. These sounds travel through the air and are transmitted directly to the ear. They move between different parts of building or from outside to inside via openings like doors, windows, vents, etc. or vibrations in walls and ceilings. Airborne noises are typically less powerful, last longer and are localized near their sources. Next is structure-borne noises. It is also known as impact sounds. These originate from vibrations within the building structures caused by impacts. Common sources include footsteps, moving furniture, dropped utensils, hammering, drilling and machinery. These noises are more intense, travel over longer distances and last for shorter periods. Now, we will be discussing about noise transmission. Noise can be transmitted in several ways. First is through air. This is the most common method where sound waves travel through openings like doors, windows, ventilators, keyholes and cracks in the wall, etc. Second is by vibrations of structural members. When sound sources are close, sound waves hit thin structural elements such as doors and partition walls, causing them to vibrate and generate secondary sound waves on the other side. Next is through structural members. In environment like factories, sound is transmitted as elastic wave motions, where compression and rarefaction of sound wave move from particle to particle within the structural component. Now, let's discuss what is transmission losses. When sound wave travels from one area to another, its intensity decreases. That is known as transmission loss. This loss is measured in decibel. For instance, if sound levels are 60 decibel and 40 decibel on either side of a wall, then the transmission loss is 20 decibel. Let's discuss some of the key points about transmission loss, which includes Transmission loss indicates the reduction of sound intensity in decibels. It also shows the effectiveness of sound insulation in barriers like walls, doors, etc. is measured by the transmission loss of airborne sound passing through them. Transmission loss depends on the materials and construction methods used. Transmission loss varies with sound frequency and should be evaluated across a broad range of frequencies. Now, we will take some acceptable indoor noise levels. Acceptable noise level inside building depend on factors such as noise nature, fluctuation timing, background noise and the building type and use. Acceptable noise level in various buildings are outlined as, for example, if the type of buildings having radio and TV studios, then the noise level is in the range of 25 decibel to 30 decibel. If it contains music room, then noise level will be 30 to 35 decibel. If there is hospital and auditoria, then noise level would be 35 to 40 decibel. If there is an apartment, hotel and homes, then noise level would be 35 to 40 decibel. If there are large public office, banks and stores, then noise level would be 45 to 50 decibel. If there are restaurants, then noise level would be 50 to 55 decibel, whereas in factories, the noise level would be 55 to 65 decibel. Actually, sound insulation reduces sound levels passing through building components distinct from sound absorption. Sound absorbent materials minimize reflected sound, while sound insulating construction block sound transmission. Porous sound absorbers are poor insulators, whereas hard materials used for insulation are poor absorbers. Sound insulation should be achieved using suitable materials and methods. Desired level of sound insulation between rooms are as following. Situation is between living room in one house or flat and the living room and the bedroom in another. Then overall insulation would be 50 decibel. Elsewhere between houses or flat, then it would be 40 decibel. Between one room and another in the same house or flat, then overall insulation would be 30 decibel. If between teaching room in a school, then overall insulation would be 40 decibel. If between one ward and another ward in hospital, if there is a normal ward, then overall insulation would be 40 decibel. If there is extra quite special ward, then overall insulation would be 45 decibel. Now let us discuss some of the sound insulating material. Firstly, non-porous rigid partitions. Sound insulation of plastered solid brick masonry walls increases with wall weight per unit area. Doubling the weight raises sound insulation by 4 to 5 decibel. Excessive thickness increases offer diminishing returns. Second one is porous rigid material. Porous rigid material like concrete masonry have higher insulation than non-porous equivalents. Plastering on one or both sides enhances insulation. Next is non-rigid or flexible porous material. Felt and mineral wool provide low sound insulation alone but can improve overall insulation when used with rigid material in composite construction. Now, we will take one by one the barriers which are used in home construction. For example, wall insulation, that is the vertical barrier. Proper wall and partition design insulate sound effectively. Type of wall construction for sound insulation include rigid homogeneous wall, that is made of stone, brick or concrete with plaster. Sound insulation increases with wall thickness and weight. Next is partition of porous material. Rigid porous material like cinder, concrete offer higher insulation than non-porous options. Non-rigid material like felt can be combined with rigid material for added benefit. Next is double wall partitions. These consist of plaster or fireboard faces with sound absorbing material between supported by minimal wooden studs. Next is cavity wall construction. It is ideal for soundproofing with a minimum 5 cm air gap or resilient material between wall leaves and tied with light butterfly wall ties. Now we will discuss some horizontal barriers that include floors and ceiling insulation. Floors and ceiling insulate against airborne and impact sounds. Rigid materials like concrete offer good airborne sound insulation but are less effective against impact sounds. Some of the key features for soundproof floors and ceilings include resilient surface material, thin concrete skids with soft finishes, carpets etc. dampen impact noise by 5 to 10 decibel but have little effect on airborne sound. Concrete floor floating construction. An additional isolated floor with mineral or glass wool and waterproof paper provides good impact sound insulation. Next is timber floor floating construction. Employing mineral wool quilts and resilient mounting improves impact sound insulation with additional sound or ash pugging for effectiveness. Timber floor with suspended ceiling and air space. This design attenuates airborne and structure-borne sound using resilient mountings and heavy independent ceilings for maximum insulation. Next is skirting. Skirting with minimal floor wall contact improves insulation using air gaps or resilient material to reduce contact area and enhance soundproofing. Now, we will discuss the another aspect of our session, that is ventilation. What is ventilation? It refers to the process of supplying fresh air into an enclosed space and removing stale or contaminated air from it. This exchange of air is vital for maintaining a healthy and comfortable indoor environment. Ventilation can be achieved through natural means such as windows and vents, or through artificial or mechanical system like fans and HVAC units. Now, why this ventilation is necessary? Let us speak one by one. First is creating air movement. Ventilation helps maintaining a continuous flow of air within a building, enhancing comfort and reducing stagnation. Next is preventing carbon dioxide buildup. Adequate ventilation prevents the excessive accumulation of carbon dioxide, ensuring a healthy environment for occupants. Avoiding flammable gas concentrations. By circulating air, ventilation reduces the risk of flammable gas or vapor concentrations which can be hazardous. Next is reducing dust and bacteria. Proper ventilation helps in minimizing dust and airborne particles that may vary or carry bacteria, contributing to better indoor air quality. Eliminating odors from decomposition. It prevents unpleasant odors resulting from the decomposition of building material by ensuring the constant exchange of air. Removing unwanted smells. Ventilation effectively removes smoke, odors and foul smells generated by building occupants, contributing to a more pleasant environment. Dissipating body heat. It helps in dispersing the body heat emitted by occupant, thereby maintaining a comfortable indoor temperature. Preventing moisture and condensation. By reducing humidity levels, ventilation prevents the condensation and deposition of moisture on walls, which can lead to mold growth and structural damage. Avoiding suffocation in crowded spaces. In spaces like conference rooms, cinemas and large halls, proper ventilation is crucial to prevent suffocation and ensure a supply of fresh air for everyone present there. Now, we will discuss some of the functional requirement of ventilation system for human comfort. Basically, ventilation systems are crucial for maintaining a comfortable and healthy environment in enclosed spaces. These systems need to meet several function requirements to ensure optimal air quality and comfort for occupant, which includes air changes or air movement, secondly the humidity, thirdly the quality of air, and lastly the temperature. Now we will discuss these one by one. First one is air movement and fresh air supply, which include the rate of air changes and air volume requirement. So, in any space where people work or live, the air must be circulated or changed at an appropriate rate. The minimum necessary change in 1 per hour, while too frequent changes, that is more than 60 per hour, can cause discomfort due to the heavy velocity of air. Optimal air changes can be facilitated by cross ventilation in naturally ventilated buildings and by fans or other mechanical means in artificially ventilated buildings. Air volume requirement. The required volume of fresh air varies depending on the activity and the occupancy of the space. For example, the living room and the bedroom typically need a minimum of 3 air changes per hour. The required volume decreases as the per person space increases, with standards adjusting based on the type of building and its use. The volume of fresh air required for the removal of body odor is influenced by the air space per person. The volume decreases as the air space per person increases. A rough guidance can be taken from the following table, in which air space per person is given and the fresh air supply per person is required. For example, if the air space per person is 5.5 meter cube, then the fresh air supply per person in meter cube per hour should be 28.5. For 8.5 air space per person, the fresh air supply per person should be 20.5 meter cube per hour. For 11 and upwards, fresh air supply per person should be 17 meter cube per hour. Indian Standard IS 3362/1977 recommends the following value for residential buildings. Firstly, living room and bedroom. In the case of living rooms and bedrooms, minimum of 3 air changes per hour should be provided. Kitchens. Large quantity of air are needed to remove the steam, heat, smell and fumes generated in cooking and to prevent excessive rise of temperature and humidity. However, for the requirement of kitchen in cooking is done for a family of not more than 5 persons, minimum rate of ventilation of about 3 air changes per hour should be provided. In bathrooms and water closets, considerable ventilation of bathroom and water closets is desirable after use and the equivalent of 3 air changes per hour should be provided. Next are passages. The period of occupation of passages, lobbies and the like is very short, and as such no special consideration in designing their ventilation system. Next we will discuss about humidity in air. Humidity refers to the presence of water vapor in the air. Relative humidity is measured as the ratio of the current amount of water vapor to the maximum possible at the same temperature. When air is fully saturated, the relative humidity is 100%. For comfortable indoor condition at 21 degrees Celsius, the relative humidity should ideally be between 33% and 70%. In hotter conditions, lower humidity and increased air movement are necessary to efficiently remove body heat. Next is air quality. Ventilation air should be devoid of contaminants such as odors, organic and inorganic particles, and harmful gases like carbon monoxide, carbon dioxide and sulfur dioxide. It is crucial that ventilating air does not originate from pollutant source like chimneys, kitchens or waste areas. Air is considered clean when it contains less than 0.5 milligram per meter cube of suspended impurities and less than 0.5 ppm of sulfur dioxide. A CO2 concentration of more than 0.06% is deemed unhealthy, with levels exceeding 0.1% becoming stifling. Proper ventilation must contain CO2 under this threshold to ensure the health, efficient fuel combustion, and preservation of building materials. Next is the effective temperature. The concept of effective temperature is essential for achieving thermal comfort. It should be adjusted so that incoming air is cool in the summer and warm in the winter, maintaining an indoor-outdoor temperature difference of no more than 8 degrees Celsius. Effective temperature is an index that combines the effect of air movement, humidity and actual temperature into a single value reflecting the temperature felt by humans rather than the measured air temperature. This makes it a crucial factor for comfort, especially in varying indoor activities and physical condition of occupant. Typically, the effective temperature should be around 20 degrees Celsius in winter and 22 degrees Celsius in summer to maintain comfort. Next, we will talk about systems of ventilation. Basically, ventilation system can be broadly categorized into two types. First is natural ventilation and second one is mechanical ventilation. First, we will discuss about natural ventilation. This type of ventilation utilizes the natural flow of air through doors, windows, ventilators and skylights to refresh indoor environment. It is typically sufficient for residential buildings and smaller structures. Natural ventilation is most effective when using cross ventilation techniques to promote air circulation. This method is cost effective as it does not require any mechanical equipment to maintain airflow. Next is mechanical ventilation. Mechanical ventilation involves using mechanical means such as fans and air handling units to enhance airflow. This system is essential for larger spaces such as office building, conference halls, auditoriums and large industrial facilities. While mechanical ventilation incurs higher cost due to equipment and energy usage, it significantly improves air quality and can cause or increase the productivity and comfort of building occupants. Now, let us get into detail of natural ventilation. In this system, ventilation is affected by doors, windows, ventilators, skylights and other openings in the enclosed space. The rate of ventilation depends on two effects. First one is wind effect and the second one is stack effect. We will discuss about wind effect. This type of ventilation is influenced by wind's direction and speed, as well as the positioning and size of openings. When the wind hits a building at right angle, it creates positive pressure on the windward side and negative pressure on the leeward side. If the wind hits at a 45-degree angle, this effect is observed on two respective sides of the building, facilitating air movement through the structure. In architectural design, it is crucial to optimize the positioning of openings to harness wind power effectively, which can vary due to its inconsistent nature. For instance, in a building with a pitched roof, the roof slope can affect the internal pressure dynamics, with more acute angles generally resulting in negative pressures. How to calculate airflow due to wind? The airflow rate, that is denoted by Q, is calculated as Q will be equal to K into area into V, where Q is the airflow rate in cubic meters per hour. K is a coefficient of effectiveness dependent on wind direction and the relative sizes of the openings. A is the area of smaller opening in square meters. V is the wind speed in meters per hour. For example, a room with 2.36 meter square openings and a 5 km/h wind inclined at 45 degree would experience about 3 air changes per hour, adequately for a moderately sized room. Next effect is the stack effect. This phenomenon occurs due to difference in temperature or vapor pressure between the interior and exterior, coupled with the vertical displacement between inlet and outlet openings. Warmer indoor air rises and escapes through higher openings, while cooler external air enters through lower openings. The rate of airflow due to the stack effect is represented by Q is equal to 640 C into A root over H into Ti minus T naught, where C is the coefficient of effectiveness with typical values ranging depending on conditions. A represent the free area of the inlet opening, where H is the height difference between the inlet and outlet. Ti and T naught are the indoor and outdoor temperature respectively. Next is the combined effect of wind and stack. In situation where both effects are present, it is recommended to calculate the contribution separately under ideal conditions and then adjust accordingly. However, in residential settings, particularly in regions with significant heat, stack effect may often be overshadowed by wind effect and can generally be discarded for practical purposes. The Indian Standard Code IS 3362/1977 provides several guidelines to optimize natural ventilation in buildings effectively. Firstly, placement of openings. Inlet should be positioned on the windward side at lower levels to allow fresh air to flow across the occupants, while outlet should be situated on the leeward side near the top. This setup helps in creating effective air movement at the occupancy level rather than just circulating air at the upper levels of the space. Second is unobstructed airflow. It is essential to ensure that inlet openings are not blocked by external obstacles like neighboring buildings, trees or signboards, nor by internal partition that could hinder the flow of air. Next is the equal area of openings. To achieve the most efficient airflow, the area of inlet and outlet openings should be approximately equal. This configuration maximizes the flow of per unit area of opening. Adaptability of wind direction. In regions with consistent wind direction, opening should be strategically placed to harness the wind force. Conversely, in areas with variable wind direction, opening should be distributed evenly around the building to ensure that regardless of wind direction, some openings will directly face the wind and other will facilitate air suction, ensuring continuous air movement. Temperature differences. Natural ventilation is driven by temperature differentials between the inside and outside of a building. In heated buildings or during cooler nights and pre-monsoon periods, when indoor temperature exceeds outdoor temperatures, it is advantageous to position ventilators near the ceiling or even in the roof, such as with cowls, vent pipes, covered roof and ridge vents to facilitate the escape of warm air and the entry of cooler air at lower levels. Window placement. Windows in living areas should either open directly onto an open space or face an unobstructed view of one. In densely built areas, creating sufficient open space may require the design of internal courtyards to ensure adequate natural ventilation. Next, we will discuss about mechanical ventilation, that is artificial ventilation. Mechanical ventilation involves using mechanical devices to ensure adequate air circulation when natural ventilation fails to meet air quality, quantity or control requirement. This system, though more expensive, significantly enhances the productivity of individuals within the environment. The main type of mechanical ventilation system include extraction system or exhaust system. This method uses propeller type exhaust fans to create a vacuum by removing stale indoor air. Fresh air is drawn into the room through openings such as turbine tubes positioned between 1.2 and 1.8 meters high or even the windows. The outlets are placed close to the ceiling opposite the air entry points. This system effectively removes smoke, dust and odors from kitchens, restrooms and industrial settings. Plenum system or supply system. In this system, fresh air is actively pushed into the room, while stale air exists through ventilators. The air enters through a location where it is least contaminated, passing through a fine screen or filter. A continuous water stream creates a fine mist that the incoming air passes through, thanks to a blower fan which removes mechanical impurities and cools the air in the summer. In winter, the air can be heated by passing it through hot water tubes. This filtered and temperature controlled air is distributed through sheet iron ducts with strategically placed branches, making it suitable for large venues like factories, conference halls and theatres. Extraction plenum system. Combining the principles of both extraction and plenum system, this setup uses extraction fans to enhance the removal of stale air, particularly effective in areas where fresh air delivery is sluggish or where there is need to quickly remove the harmful fumes as in kitchens or manufacturing areas. And the last one is air conditioning. This comprehensive system includes air filtration, heating, cooling, humidifying and dehumidifying, creating optimal condition for comfort and efficiency in enclosed spaces. These systems are tailored to provide effective ventilation in various settings, ensuring a healthy and productive environment. Now, last topic we will be discussing about air conditioning. Air conditioning refers to the process of treating air to control its temperature, humidity, purity and distribution to meet the specific needs of the space. These needs might include ensuring comfort and health for people, enhancing industrial processes or improving the efficiency of commercial operations. The purpose of air conditioning include maintaining the health, comfort and convenience of residents in a building, improving product quality in industries such as artificial silk or cotton cloth, or creating comfortable working conditions that can boost production, enhancing the functionality and efficiency of commercial spaces like shops, banks, offices and restaurants, providing a more enjoyable experience in entertainment venues such as theatres, making travel more comfortable in air conditioned coaches or airplanes. From a functional perspective, air conditioning can be categorized into comfort air conditioning and industrial air conditioning. Comfort air conditioning focuses on providing a maximum comfort for the occupants or users of the space, while the air conditioning aims to create and maintain an environment that is optimal for specific industrial needs. Based on seasonal or temperature consideration, air conditioning can be classified as summer air conditioning or winter air conditioning, where summer air conditioning involves cooling the air when outside temperatures are high, including processes like air cleaning, cooling, dehumidification and distribution. Winter air cooling or conditioning involves heating the air when outside temperatures are low, with processes including air cleaning, heating, humidification and distribution. Composite air conditioning maintains a consistent environment year around regardless of outside temperature changes. So, dear learners, we have reached the end of today's session. I hope you found it informative and engaging. See you in the next session. Thank you.